In section 8.1, we talked about what a confidence interval is, why they're important, and how to interpret them. In section 8.2, we're going to talk about how to construct and interpret confidence intervals for proportions. Okay, kind of go through the entire process. Confidence intervals for the population proportion. Recall, the standard deviation of the sampling distribution of p hat is the square root of pq over n. That's the standard deviation of the sampling distribution of p hat. Suppose we want to estimate the true population proportion of people that like Star Wars. Of course, it's 100%. Maybe not. We take a simple random sample of 200 people and find that 79% of the people in the sample like Star Wars. Explain why you cannot calculate the standard deviation of the sampling distribution of p hat. So we know p hat is 0.79. The problem is we don't know p. I don't know the true population proportion. If I knew that, I wouldn't be sampling 200 people to get an estimate. So to calculate the standard deviation of p hat, you need p, q, and n. I got n, but I don't know p, and I don't know q. That's why I can't do it. So this presents a problem. Last chapter, we always pretended that we had the true population proportion, but now we don't. So what do we do instead? Obviously, this is our estimate for that. So since I don't have this, I could just use this as an estimate. Now, it's not going to be exactly right, but it should be pretty close. This is called the standard error. When the standard deviation of a statistic is estimated from data, because you don't know the population parameter, the result is called the standard error of the statistic. So the standard error of p hat, this is just different ways of writing it, is equal to, for some reason this isn't showing up. It should show up in your notes, but the hats aren't showing up on my document. It's basically the square root of your sample proportion divided by 1 minus times 1 minus your sample proportion all over n. In general, the standard error of p hat is a very good estimate for the standard deviation of p hat. So this is a good estimator for that. Example, standard error versus the true standard deviation. Okay, so the true population proportion of people that like the color red is 40%. We take a sample of size 1,000 and estimate the true population proportion. We get a sample proportion of 35%. So the true proportion is 0.4. Our sample proportion is 0.35. Calculate the standard deviation. So standard deviation is PQ over N. Parameter values. 0.4, 0.6, all over 1,000. Can I do that in my head? Or I think, well, whatever, no sense even trying, right? Square root, 0.4, dang it, 0.4 times 0.6 divided by 1,000. 0.01549. 0.01549. 0.01549. Now, normally I probably wouldn't go this accurate, but I want to compare the standard deviation to the standard error of my sampling distribution. Calculate the standard error. So the standard error of p hat is the square root of p hat q hat over n. We just put in the sample statistics to estimate it, because in reality we're never going to know that 40%. So that's going to be 0.35 times 0.65 over 1,000. And as you can probably surmise, these aren't going to be that far off. So just 3.5 and 6.5. 0.01508. 0.01548 or 1541. 1508. My bad. Sorry. Okay. Now, granted, what I'm trying to illustrate to you is that whenever you use sample statistics to estimate the standard deviation of the sampling distribution, they're not far off. Now, of course, this was a pretty big sample size, and my sample proportion was pretty close. If your sample proportion is further off, it might make more of a difference. Or if your sample size is maybe smaller, I guess, it might make more of a difference. But in general, the standard error is a good estimate for the standard deviation. Okay. The reason I mention this is because when we start talking about the standard error of X bar of the sample means, we're gonna have problems with this. But for proportions, we're pretty good. Finding the critical values. It isn't good enough to say that 2 standard deviations in a normal distribution captures 95%. We need more accuracy. Remember, this 95% was kind of just an approximation. Find the zero scores that cut off to accurate to 2 decimal places that cut off the middle 95%. So if I want 95% in the middle, and I want these z-scores, that is 0.025 on the tails. This is the inverse normal function, and I'm just going to put in the 0.25. This will give us a more accurate z-score for that cutoff. Inverse normal, 0.025, negative 1.96. So z equals negative 1.96 to z equals positive 1.96. As you can see, it's close to 2. But if we want to get exactly 9% or more precisely 95%, we're going to use these cutoffs. These are called critical values, or z-crits, that correspond to 95% confidence. So whenever we do our formula, we're going to take our statistic plus or minus our margin of error. That is our statistic plus or minus our critical value times the standard deviation of our statistic. So we're trying to find out how to calculate these z-crits. Instead of 2, maybe 1.96 or some different values. So let's find the cutoff for an 80% confidence interval. This gets a little repetitive because these are all kind of the same. 80% on the inside, 20% on the tails, 10% on a single tail. So we kind of just put in that one tail area for each of them, 0.1. So that's 1.28. So my z-crit would be 1.28. So if I want to be 80% confident, I'm going to multiply by 1.28 standard deviation, so I capture about 80%. 90%, that would be 0.05. My bad. Usually we go an extra decimal here because it's kind of right at the halfway point. So usually we say 1.645. Z-crit is 1.645. 95% confidence, we already did that one. I don't need to do it again. That's 1.96. We want to be 99% confident. 99% in the inside. That's 1% on the tails combined. That's 0.5% on one tail. So I'm going to go up here and grab this one and just put in an extra 0. 2.58. And that should kind of make sense that it's 2.58. If we want to be 99.7% confident, remember that was kind of 3 standard deviations. So it makes sense that 99% is going to be somewhere between the 2 standard deviations and the 3. Okay? But using this technique, you can get the z-crit cutoffs for any confidence level that you want. All right, so we are almost ready to calculate a 1 sample z interval for the true population proportion. I think this is a good place to stop. We'll pick up in class here tomorrow. Okay?